COGS108 final by Kiana Dugal, Kirsten Arcinas, Marcy Fisay on e-scooter accidents. Picture this. You're running late to class and decide to grab an e-scooter because it's fast, convenient, and always right around the corner. You hop on thinking you're just about to make it to class on time, weave around countless pedestrians, and suddenly end up flat on the pavement. Those moments got us thinking. As micromobility becomes more common in cities and on campuses, are accidents increasing as well? Our research question is, how does the density of micromobility traffic, specifically e-scooter and e-bike usage, correlate with the frequency of traffic accidents across major U.S. cities? Some prior work we had found was a 6-year USF study where they compared injury rates between motorized and non-motorized vehicles and found that there were fewer injuries among motorized users. Furthermore, Kabuk et al. Had also used machine learning models that predicted e-scooter severity crashes by identifying infrastructure issues. Limitations was that they did not necessarily examine micromobility traffic density as a predictor of accident frequency and focused mainly on severity prediction and infrastructure factors. Our research differs as it investigates micromobility traffic and studies the relationship between vehicle volume and accident frequency instead of only looking at crash severity or environmental factors. We hypothesize that areas with higher micromobility traffic will experience more accidents because increased usage naturally raises the chance of collisions and rider error. Prior research highlights that unsafe riding behavior and inadequate infrastructure contributes to these risks. As more people use e-scooters and e-bikes in shared spaces, the likelihood of accident rises, especially where safety measures like bike lanes and helmet use are lacking.
Our first data set comes from the National Transportation Atlas database, an e-scooter database to be certain. It includes 207 rows and it tells us which U.S. cities have e-scooter systems and roughly how many scooters they have. It's simple, however, the downside is that it only shows availability and not how often scooters are used or whether crashes happen. So that's the reason for our second data set. It's the Micromodes e-scooter fatality database. It, once cleaned up, has 200 fatal crash cases and includes details like bike lanes, sidewalks, number of lanes, whether a car was involved, and helmet use. But the main limitation is that it only includes fatal crashes.
To merge the database, we had first standardized states and cities by using uppercase and the abbreviated version of states. We had furthermore found any relevant columns such as state or city in the name and trimmed and removed any extra lines.
For our first EDA plot, we looked at helmet use compared to the type of injury. Most of the entries have unknown for the helmet use, which means that the dataset can't really tell who was or wasn't wearing a helmet. Even with that limitation, the plot still shows that most fatal crashes involved collisions with motor vehicles, which was one of the few consistent patterns in the data.
From our second round of EDA, we wanted to see whether cities with more scooters available also see more fatal crashes. This helps us understand the main research question about how micromobility density relates to accident outcomes. Even with a small sample, this step is relevant. As you can see from our graph, fatal crashes stay between 1 and 3 across all cities, and the spread does not change very much as availability increases. So at this stage, there's no clear pattern between scooter availability and fatal crashes. For our third round of EDA, we discovered that Florida has the highest number of fatal e-scooter crashes in this data set, and California and Georgia follow with 4 cases each. This suggests that larger states, or those with heavy micromobility use, may see more incidents. We really wanted to see the distribution of e-scooter crashes throughout major states in this EDA. The spread of values shows that crash counts vary widely by state and are not evenly distributed. For ethics and privacy, the demographics are recorded in our dataset involving micromobility accidents, so there may be concerns with privacy if the subjects were not informed. We also used public dataset from governmental institutions, and so datasets not including the full names of individuals were used to keep them private. Concluding, we studied whether cities with more e-scooters also have more fatal e-scooter crashes. We did this through merging 2 datasets together. We discovered that fatalities remained low even where availability varied widely. There is some missing information that hindered our process, such as helmet use and infrastructure factors. Additionally, safer conclusions require richer public data on usage and non-fatal injuries.